looks like we don't have any questions. So what we can do is go ahead and go over some of our testing. So let me open up our file explorer here. Again, we have our app.py function and then our deploy.py function. This is going to actually deploy the contract. And we'll call this in just a second just to make sure everything compiles correctly. And then we have our test app, and this is using Pytest along with Beaker and our Algo SDK in order to execute some testing on our contract. And we'll be going over everything that's happening in this Pytest as well. But before we go into the nitty gritty details of it, let's first do some sanity checks. So the first thing we're going to do is head on over to our build and deploy tab, and we're going to hit the play button, and we're going to make sure that our app actually compiles here. So what it's doing, it's building the app, and then it's calling deploy.py in order to actually create it. So we've now seen a deploy.py is called. So let's do an algo kit localnet or and take a look at our latest transactions. Now we can see here we have one transaction that created application ID 1, and we can see we set all of our global states to empty values. And you might notice that we have our types as uints and then our type as bytes, but byte shows as a 0. On Algorand, an empty byte string and a 0 uint64 are actually the same value. So that's why it's coming up as value 0, even though it's a bytes type. When we actually populate this type, that'll get probably set to the address of the byte slice as we would expect it. Okay, so now we verified that we can successfully compile our app. So I want to verify that. We can go over to our artifacts. We could take a look at our contract JSON. This contains all of our methods. And then we could take a look at our application JSON. This contains a little bit more information pertaining to typing, our source code, what sort of stuff we're saving in global and local state, etc. But the core things here are the approval program. So this is the actual on-chain logic. If you go take a look at Dapflow, we can see that it's been deployed successfully. So we've compiled here our artifacts. We've deployed on Dapflow. It's bigger, so it's easier to see. Deploy on app Dapflow with that approval program. So now we can go ahead and run our tests. So first, let's take a look at what our testing will actually look like. So here on VS Code, if you come on down to our testing tab here, and then we can click this play button. That will do is execute our test using Pytest. And we can see here that all of these tests have executed and ran successfully. So now let's open up this test file and take a look at what we've actually done here. So our imports, we can go ahead and safely ignore these for now. We'll talk about them as we encounter them. But basically, the main thing here is we're importing Pytest. We're importing various things from Algo SDK and Beaker as well. Now, one thing I want to mention, this is probably not best practices for writing Pytest tests. As you get more complex test structures, you don't want to be using things like global variables. You want to properly be passing the types in your fixtures. In our case, for simplicity's sake, especially for those that aren't super familiar with Pytest, I just use things like global variables here, just so it's a little bit easier to make sense of what's actually going on. But we're still going to be using Pytest to actually execute our functions. So let's talk a little bit about the kind of overall layout of this file, and then we'll go into what the actual methods are doing. So we've broken it down into two main parts. We first have our fixtures, and in Pytest, or this is sometimes used in other testing frameworks as well, a fixture is essentially a helper method that we want to call in order to set up the state for our test. So what we want our fixtures to do, just taking a look at the names here, we have a fixture for creating the app, fixture for opting in, fixture for starting the auction, for setting our first bid, and setting our second bid, and for ending the auction as well. And then our claim bid and claim asset fixtures as well. So these are the things that actually do the things for our test. And then down here, we have our actual tests where we're just, in my case, we are asserting that our values are equal to what we'd expect them to be. And so if we come up back up here, so the main layout is we have our fixtures up top. And these are basically our helper methods, actually doing the on-chain stuff. And then our tests, which are more or less just the assertions, making sure everything worked as we expected it to. So now let's go ahead and take a look at our fixtures and what they're doing. So our first of which is called create app. And in order to specify this as a fixture, we call at pytest.fixture decorator, and we scope it to the module. This is basically just saying this is a fixture that we want to use here in our test app module. And in create app, what we want to do is create the application and then save it. So the first thing we're going to do is get the accounts on our local network. So here in our testing, we're going to be using our local network. So as part of AlgoKit, we have our local network here that we've seen on DAppFlow, and we can make sure it's running AlgoKit local net status. Then you go ahead and see that we have a local net on round 10. It's running standard V1 network, time since last round, yada, yada. So we verified that we're actually running our network. And so what we also want to do is we have this, I think that's the correct command, run AlgoKit goal account list. Let me, it's a little bit easier to see. What we could do here is we can see that we have some accounts that are saved on our local network. And so what we want to do is in our Python code, programmatically get all of these accounts. What I'm doing here is there's this .get accounts method that's provided by Beaker under the sandbox namespace. So you're calling sandbox.get accounts. And this is basically saying get all the accounts in our local network and put them in an array. And then we're also using a Lambda function in our sorted method to sort them by amount. So this accounts will contain an array of all of our local accounts on our local network, sorted by which ones hold the most amount of algo. In our case, we want our creator account to just be popped off the array. And so we're just going to call array.pop. And so now creator account is going to be a account object. And in this account object, it holds an address, its private key, and what we call a signer. And a signer is basically a function that tells Beaker or tells our SDKs how I want to sign the transaction. So on this creator account object, this signer, what it is basically doing is saying, whenever we want to sign our transactions, call this signer function. And what this is doing is signing each of the transactions with the creator account private key. Okay, so we've gotten our creator account. And now what we do is instantiate what's called an application client. And in our app client, this is basically the interface we use for interacting with our smart contract. So to interact with the Algorand network, we use what's called an AlgoD client. To interact with a specific contract, we use what's called an application client. And to initialize our application client, the first thing we do is specify which app we're going to be interacting with. And so in order to do that, we need to read in our application JSON. So as part of our artifacts that we generated, we have this application JSON file, and this tells Beaker all the information about the contract that we want to know, including the source code and our methods and the state types, et cetera, et cetera. So what we're basically doing is passing in the string of that JSON. So we're calling open application JSON.read, passing that to app. For client, this is specifying what our AlgoD client is. And again, we're using the sandbox helper method get algod client to connect to our local network. And then finally, we're passing in our signer. In our case, it'll be the signer for our creator account. Now to create the contract, we simply call appclient.create, and I'll go ahead and create the contract. And now our accounts, creator account, and app client are all global variables, so they'll be accessible to us in our other fixtures and tests as well. So now in our opt-in fixture, what we basically want to do is create an asset and then opt that our contract into that asset. So we're going to be using our Atomic Transaction Composer. If you attended the first session, this works very similarly to the JavaScript Atomic Transaction Composer, because of course we're working with Python. So what we're going to do is we're going to form an ASA creation transaction, and it's going to be a transaction with signer. And for our actual transaction, we're calling transaction dot as the create transaction, saying the sender is going to be our creator. Our total is 1. This is just going to be NFT, 0 decimals. So this is not going to be divisible, not going to be frozen. Our unit name is BASA. Asset name is Beaker ASA. And our suggested parameters. And again, this is basically the recommended things that we want to send to the network with every transaction. We're going to get it by calling appclient.get suggested params. And then our signer is going to be a creator account signer. And so now we have a asset create transaction that can be signed by our creator. So we're going to go ahead and add that to our atomic transaction group. And then we're going to go ahead and execute that atomic transaction group. In our case, it's only one transaction, but it's still generally easier to use Atomic Transaction Composer even if you only have one transaction. Then we're going to call execute and get the transaction ID that we sent. And so now we can use that transaction ID to get the transaction information. So on our algod client, call pending transaction info, pass in our ID. And in this transaction information that we get from algod, it'll have this asset index field that specifies what the index of the asset we created is. And we're going to save that in our ASA variable, which again is a global variable. So now we've created our ASA. We're going to go ahead and fund our application. So we're sending it 200,000 micro algo or 0.2 algo. 0.1 is for the account minimum balance. So every account on the ledger needs 0.1 algo. And then we also need an additional 0.2 or additional 0.1 for the ASA. So every ASA in our account increases our minimum balance requirement. So how much algo that account needs to hold by 0.1 or 100,000 micro algo. So we're sending a total of 0.2 in order to cover both the account minimum balance requirement and our ASA minimum balance requirement. So to do that, we have this app client.fund helper method, and this basically sends 200,000 micro algo from our creator to our application. And now that we have our app funded, we can go ahead and call our opt into asset function. And one important thing that we're doing here is we're getting our suggested parameters, and then we're doubling the fee in order to cover the inner transaction. So if we go ahead and take a look at opt, we can go ahead and see in this function, we always have an inner transaction. The fee here is 0. So we need to double our fee here in order to cover that inner fee. So we go ahead, get our suggested params, override the minimum fee or override our fee by doubling our min fee, and then simply call opt into asset. And our argument here is our asset. So we're passing in asset equals ASA. And now because we've changed our suggested parameters, you have to explicitly provide it. So saying suggested params equal SP. So now at this point, I will actually call the contract, call this opt into asset method with one argument being the asset that we created. So now at the end of this fixture, our asset will be opted in and we're ready to actually start the auction.